Hi, good afternoon.
Hello, hello. Can everyone hear me and see my screen? I couldn't hear you before.
Yeah, we hear you.
Yes.
Yep.
Oh, I can't hear you guys. Hold on a second. Okay, somebody say something now.
Hi, John.
All right, I'm in business. Thank you. Sorry about that. Sometimes my computer just goes out and I can't really tell what's going on with it. But we're fixed now. So I think I'm going to go ahead and get us started. I'm going to make sure I got everybody. I got Ben. John. See Tyron, Christian. Okay. All right. Well, that's what we'll run with for now. I don't generally take off for attendance when you're in a virtual class. We're not in a virtual class, we're in a blended class, but you know, we don't have to be together all the time since we are recording. So I want to make sure that we are recording. It says that we are recording. Yep. And so all we have today is module 1 available. And so this class is called Smart Home or Smart Grid Home Integration. And so really what it's about is it's about learning energy efficiency in order to build or to look at a house. So it's not always going to be about I'm going to build a brand new house and this is the way it's going to look, because you may not be able to afford to do that or design something like that. But it's also about if you have an existing home or you just purchase whatever you can get, but you still want to be energy efficient. It's understanding what it is and what those things are that create the issues. And it really boils down to this whole concept of heat. So welcome to the course. If you don't know me, my name is John Rodabush. I am the program chair. I see Ethan in here. I see a couple new faces. I will get to see you guys on Wednesday, January 26th, where we'll be able to meet for the first time. And we're going to be pretty busy in this class. When we get to campus and we get to the Energy Center, one of the reasons why it's good for us to go over some of this information first. Of course, today's first day is pretty easy, pretty lightweight. We'll go over a lesson together, get some foundations. Mondays will be virtual also, but it is going to be a lot more information, a little bit tougher. And you really don't want to miss it because you can get lost, because we're going to be learning about how to do heat loss, heat gain calculations. And we're using a textbook that I have in here. So you're allowed to borrow a chapter or two from a publisher and use it in different books, especially if you're not going to use the whole book. So we're just borrowing from Cengage a book called Heating for Renewables, but it's a book about hydronics. We don't care too much about hydronics. We'll talk about it. It'll be something that's part of renewables, but that's not our sole purpose. So that whole textbook is like 1,000 pages, and I'm not trying to make anybody pay a bunch of money for a huge 1,000-page textbook. So we're going to use the first chapter and the second chapter, and then we'll be switching over to some other e-textbooks. So you should not need to purchase a book for this course. So if we want to click right here, we can click on our syllabus. And we can see all the basic information that you need to see when this class is and when my office hours are. My office hours are Tuesday and Thursday, 8:30 to 12:30 p.m. Generally just email me or try to set up an appointment through advising or request you can call Griffin Hall, call the office 52229, and the receptionist there can put you on my calendar too, for whatever reason. So there really isn't any instructional material supplies that you need to have. I have all the stuff. I have the e-text material. I wish we had a nice, great, big, fat book that we could use that was perfect, but that's not always the case. So I've used different books in the past, and then I end up with kind of a bunch of different material that we put together. So you can see that the grading scale, sorry about that, professionalism labs 20, 20, 10 on projects, 20 on homework. You'll have a quiz midterm and a quiz final that you'll take. Those are only worth 5. And then, of course, your regular midterm and exam grades are going to be 90, 80, 70, 60. Same as usual. And so we'll scroll down, watch your eyes here. You'll find your course calendar down here. You'll see that we're starting off with heating with renewables on week 1. You've got 8 weeks here. So that's where we're going to talk about residential energy basics today. And then I also consider next week part of week 1. We'll start getting into the space heating, and then we'll discuss about when you're going to take this quiz. We'll see how far we get. But that's all that we're going to do. The space heating, I don't even want to show you right now. If you've ever heard, it's hard. It's calculations, but I'm going to go through it with you very slow. And then what's really nice is on Wednesday, January 26th, Wednesday, you will be able to come to class at the Energy Center, and we're going to start doing some application with the stuff that we're learning. We're going to start measuring the room, measuring the wall, doing the calculations that we need to do using our thermal imaging equipment, and starting to map out the heat loss, heat gain of a building, and understand how to do an energy audit. So that's pretty much it. I don't like to spend a whole lot of time on the syllabus unless someone has some questions. Really, all you need to worry about is whatever I have listed under week 1, and then once you see week 2, whatever's listed under week 2. So when we come into week 1, we can get there a couple ways, but we can click right here. It's a really short lesson. It'll take us, I'm not sure how long it's going to take us, but we need to have a discussion. So I'm trying to work with you guys on getting you to understand some of the basic concepts of energy, the law of thermodynamics, and the concept of heat loss and cost to benefit ratios on our fuel costs. So we're just going to get started on that and think about some of those concepts. You have your
John,
yes, go ahead.
I'm seeing the page says it hasn't been unlocked yet.
Oh, let's do that. It has not. That's easy enough. We click this button here. There you go. Thank you for letting me know that. Appreciate that. And I also think someone else showed up here.
I just showed up.
Okay. Is that Tyron? I can't see who. Yeah, there you are.
Yes, sir.
All righty. Yeah, I don't expect to take up too much of your guys' time today with this being our first lesson. And I know how tough the next one's going to be, but we need to set some just basics down before we get into too much. And then we need to spend some time on Monday going over what those calculations are, and it's going to be tough. But once we get there on Wednesday, you'll know what to do. So you only have one assignment right now, and it's a real short, very easy assignment. So if we click over here, you're going to see the chapter 1 book that we're going through. And I like to go with this book. I almost have to read it to you because it's tough. Now, this first section, we'll have a chance to look at it, and I'll be able to go into more of a discussion from the material, but the other one has got examples and things. And so PowerPoints do not work very well in this area. And it's also something that I need to make sure that you do go through, because if you just kind of blow this off and don't go over it, you know, at least you've got me and you've got a recording where you can hear me talk about the material. You can listen to it in your car or something. Make sure you're understanding what's going on. Your homework assignment is not going to be very hard at all. It's going, those are the PowerPoints, which I'm not going to use, but they're good cliff notes. There's 24 of them, but they're just way too short when you're going through this, and you know, there's no real good information there that's going to help you sustain the understanding of what we're trying to say. So when we look at our homework, you should have more than one attempt to do this. So it's very easy. It's just going to be an introductory homework. They will be getting harder. We have a lot of spreadsheets that we've got to work on when we do these heat gain calculations. So there's only like 12 questions. You should be able to get through that in today's lessons, no problem. But I primarily want to just get us going. And let's see here. Oh, let's just go back. There. One more. I just want to get us going on our lesson. And it's not very long. It's only 17 pages, but it's going to feel a little longer than that. Our other chapter is still only maybe 40 pages, but it feels like it's 100. It's just a lot of information. So the objectives of what we're trying to do here is we're trying to first understand human comfort. That's one thing, and understand how the body loses heat. Some very basic concepts with that, and then get ultimately into understanding that we've got a limited amount of options that we can do to help people be more comfortable. So let me ask you guys this question before I start getting into too much of this stuff. What do you guys like to put your thermostats at in your house?
78.
Really?
78?
It's
Oh
like a
my-
terranium.
Yeah.
That's warm. You cold. Well, my wife would love 78. I know that. Anybody else?
Mine's
Mine
at
at, like,
68.
Yeah, like 65.
68,
71 or
function with-
72.
72.
70.
Necessarily function. I can't do it. My body's stiffing up too bad.
Oh, I hear you. Well, I prefer 73. I'm pretty comfortable at 73. But we just heard all of us say different numbers. And that's because a person's energy usage really depends upon their comfort. When you're thinking about it in that term, you know, we've talked about maybe putting a solar system on a house and doing things with other people and some of our other classes maybe. But at this point in time, you know, we're all kind of thinking everybody wants their temperature like me. So if I have my temperature set to 78, I will be paying $800 a month in an electric bill. If I have my temperature set down to 60, I'll be freezing. And part of that has to do with, it's not just me, it's my house. It's the building that I'm in. It's the thermal environment that I'm in. So there's another area also that we need to keep track of, and less of us know about it, is the humidity levels. So we like the humidity to be between 30 and 40%. If you feel your house is getting to be like 65%, 70% humidity, that's when you're starting to feel like the sweat beat up on your face or on your hands, things like that. It's too hot. You want to get it down. If you get it down to where it's like 20 or 15% humidity, that's where you might have a dry cough, or your nose might dry out, or you can't breathe. So that's the idea. How do we figure out how to get each one of us in the building that we are in to be comfortable and be the most energy efficient as possible? That's the question that we're looking at, or starting to look at. And it's a very complex question, but it can be answered and we can figure it out. So the textbook moves on and starts talking about domestic water heating is a big part of and it is, it's an energy hog. Your biggest energy hog is going to be your heating system, whether you're using electric heat or natural gas or some other type of heat, same as with your air conditioning. I mean, we all use pretty much the same type of air conditioning systems anymore, but you will see that each one of these has a load in BTUs that it requires to use. Now we talk about stuff in BTUs a lot, and we can convert BTUs into watts, and we'll do that a few times because that helps us understand, well, if I need this many BTUs, then I need this much solar generation if I want to do, say, solar in watts. So that's kind of what you're learning to figure out, on top of learning how to create a house or take an existing house and learn a better way to keep you warm. It could be something as simple as hanging quilts over your window. If you came to my house right now, I have quilts hanging up over all my windows, and it's because I have ginormous windows, which are terrible. I lose heat through my windows like crazy. It costs me money. It's inefficient. It's bad, but I like windows, and I'm going to have to pay for them. But right now it's a little bit colder outside. Actually, it's not bad today, but normally it gets a little bit colder, and I don't want to lose all my heat through my windows. So you can do things as simple as just hanging blankets or hanging quilts. But that's not necessarily good enough if we're wanting to talk about doing things in a efficient way. So you're going to read through here about the oil embargo and the shock of that. That isn't very important to this lesson here. But what it did do is it did bring in the interest into renewables. And then we saw that interest quickly disappear when we saw the 80s. So he runs down here into the 80s and he talks about, skepticism of renewables, and it was considered, long story short, a hobby in the 80s. And then we enter into the modern age where we have better systems that are, and also the price of oil. When we see the price of oil go up, then we see a larger interest in renewable energy because all energy costs are starting to go up. And I expect there to be a continued interest. A lot of it is in just the cost. Some of it is in the concern of climate change and the worldwide push. But what we know is the worldwide demand for energy is growing. And so we've seen there are more and more people out there that are wanting to get into building renewable energy systems. Your chancellor for the college is one of them. He just finished putting a solar system on his house from people who graduated from the energy program. So, you know, a company that they work for did his system. So, you know, it's pretty neat to see that. And these systems do work, but that's only part of the story, right? Because we can put solar thermal collectors on our house, we can put heat pumps, we can put solar panels, but if it's not making enough energy to replace the lost energy, then we're going to be cold or hot or uncomfortable. Okay. So what we want to do is make sure we understand that when we are trying to size or design a system, or if we're trying to help someone reduce their energy costs, that they are getting a return of investment, that they are able to look at this and go, okay, if I put this much money in insulation in my house, what am I going to get back out of it? How much is it going to save me versus how much is it going to cost? So a lot of that stuff is related to design and whether it makes sense, whether someone's done something like done the unit cost of energy, because one person can say something versus another. 10 years ago, that might have been the way it was, but now everything's changed because the unit or the price of cost of energy has also changed. Is there any questions or comments so far?
No.
Okay, good. Well, that's all right. I got to keep rolling with this anyway in this fashion. So let's talk about comfort. So we know that the primary objective is comfort. And when we're looking at people, we lose heat through our bodies. So as we're sitting there, our bodies are constantly losing heat. Where do you guys feel in your house? Where do you feel the most comfortable?
Bedroom.
Where's that? In your bedroom? In a very specific room. Are there rooms in a house that are, I mean, they are, right? There are rooms that are colder than other rooms. And why is that? What could be a reason?
Spend less time in those rooms.
Well, true, but let's just say you bought a new family home.
Bigger spaces.
Air spaces. Yeah, the zones. Bigger spaces. There we go. Bigger spaces are harder to heat. Was that so? That means say, well, maybe I shouldn't get a house that's open. Well, that's not necessarily true, but a bigger house is a bigger space that you have to also heat. But let's say we're looking at two different homes. One's a 2,000 square foot home, another's a 2,000 square foot home, maybe even a third 2,000 square foot home. But one is more comfortable than the other in the way that it holds heat, what would be wrong with those other buildings that would make that, even though they're the same size?
Could one house have more windows or bigger windows?
Windows. Yep. So we're thinking simple. Remember, this is day one. We got to go back to some basics. So windows, too many windows. Windows do not hold or slow down heat as well as an insulated wall. I think we all know that. What else though? We got windows. What else do we have that we have to worry about?
Could it be the direction that the house is towards the sun?
Okay, one, for you said for its design, what its purpose is, and what else was said there? I heard two expressions, two answers.
I was just saying, I guess the direction of which the house is facing the sun.
Sure. I mean, that's a big one with my house, because I've got all these windows and I've got a passive solar design to it, not 100% passive, but it works. My house heats up good. So if you've got lots of windows, you've got one wall of the house being shown on by the sun. But what do we depend? What else does a house have besides windows that will leak air?
Doors.
Doors. Yes, doors are a big one. You got to make sure that your doors are not leaking a lot of air, weather stripping and everything. So, we're talking about very simple things that can save enormous amounts of heat from leaving your house, or heat that you either lose heat that you don't want or you gain heat that you don't want. That's what we say. We don't get confused and go, well, we're doing cool or hot. We're doing heat. We say heat loss, heat gain. You want heat loss or you either want heat gain. One of the two. So we also have other things that we have in our walls. What do we have in our walls that prevents the loss of heat?
Insulation.
Sort of like insulation.
Right. Very good. Insulation, Ben. Yep. Insulation, everybody. So do you think that you would go buy a house that doesn't have any insulation in it? Let's say it's got walls with drywall up, painted walls. You'd expect there to be insulation behind those walls, right? But some of these houses, the insulation is either so old that it's pretty much just turned into dust and fallen down to the bottom of the floor, or they didn't put it in there, or it is in there, it's just not thick enough, or it doesn't have any. Like in my house, I have insulation in some of my house, and some of my walls are just made of wood because it's got cabin-like features. It's cold. It's not the best. Insulation's better. It is better. So let's move on a little bit. So what we're talking about is that a person could be very uncomfortable based upon the type of house that they're living in and the type of comfort level that they want to have. This is saying that a normal adult engaged in light activity generates heat rate at about 400 BTUs. If you're sitting on surfaces that are colder or hotter, then you're going to lose more heat more quickly or gain heat and sweat. And the same with the room. If the room is making more heat, you're going to not be at what we call thermal equilibrium. So our body gives off thermal radiation, gives off heat. We can see that with infrared technology, infrared cameras. If we were shining them on each other, we'd see that we would be glowing, red and everything else around us would be blue, is because we're hot. Our body makes heat. But we adjust, right? Our body can adjust. So when we are experiencing different temperatures around us, we can suppress what's called convection. So when we're looking at this lesson, I want you to try to pay attention to these words in bold type. There's just a few of them, you know, there's about 5 or 6 of them in this lesson, because we're talking about some of the concepts of the evaporation cycle. We're talking about how heat rises and how it changes things. And we need to understand that as we're losing heat through our house, you know. So convection heat loss can be suppressed if we sweat, you know, or go through the process of evaporation. So we can go through different ways of trying to be comfortable, but ultimately we want to try to figure out in each area, in each room, the different zones of the building, what is going on in that room and what can I do to make that room better? And do I even care? Do I want to heat those rooms because those rooms are going to cost me money? If nobody's in those rooms, maybe it's fine that they're colder because it would be cheaper that way. Okay. So we're going to move on down to this first law, this first common law. And I want you to think about it. Heat always moves from an area of higher temperature to an area of lower temperature. So if we were to look at this example, this is a solar thermal tank system. In this solar thermal tank system, we would see sunlight shining down on a solar evaporator. The cold water that's coming from the inside of the house, it's what we've already used. It's just water, tepid, warm, cold water, is pumped into the bottom of this. And now the sun shines on a solar thermal panel. You may not know much about solar thermal panels, but what we know is the water starts getting hotter and hotter and it rises to the top. Then that runs down into our tank through this heat exchanger. And then this would be like a solar thermal or even a boiler system. You could have a system like this. Now, really all we're doing is pumping hot water through radiators or heat emitters throughout the house. And we can see as we pump it, the heat is moving up and out and away. So this is going to be the area of high temperature, and it's going to rise to a lower temperature, which is going to be basically around it or up in the other top corners. And so we'd want to put probably a fan right here in this building to blow this heat back down in a way that you could enjoy it. Okay. Another concept that we want to try to understand is temperature differentials. So if it is 73 degrees outside, is my furnace probably running?
No.
Yeah, I mean, probably not, right? I mean, if it's 69, 70, 73, it's probably off. That's because we're at thermal equilibrium. That means that you have the same temperature outside as you have inside. And so there's really not much going on of heat loss or heat gain. So everything is great. It's when we start to see a great temperature difference that we have the heat transfer problem. the greater the temperature difference, the faster the heat flows. So in other words, the heat's going to move around the house and try to warm it up as fast as it can when it's really, really, really cold. But you got to have enough heat to be able to do that. Okay. So thus, the temperature differential across the material were doubled. The rate of heat transfer through the material would also double. So those are just some simple concepts. So we have 3 modes of heat transfer that we want to pay attention to. We want to pay attention to conduction, convection, and thermal radiation. So conduction is the type of heat that occurs through solid materials. So metal objects can go through conduction, or we feel the heat in a solid material. And all material has a concept, an index that we'll come back to several times. So this index is called the thermal conductivity. So the higher a material's thermal conductivity, the faster heat can pass through it. So we want to make sure that we are aware of how much heat we're losing through certain materials. So one type of material is going to lose heat faster and more than another type of material. That could be insulation versus wood or concrete. The rate of heat transfer by conduction is directly proportional both to temperature differences across the material and its thermal conductivity. It's also the thickness of the material. So if we have thicker walls versus thinner walls, all of that adds up into our total thermal conductivity. And that's what we'll be doing when we start to get into, let's keep moving on here, when we start to get into the heat gain, heat loss calculations. Heat gain, heat loss calculations are going to require us to look at a lot of different things. We're going to have to look at the drywall. We're going to have to look at what is the thermal conductivity of that solid material? What is behind the drywall? Is there insulation? We could use an infrared imager to see that. Is that wall warmer or colder? How many studs are in the wall? Because they take up space, and wood has a different thermal conductivity than insulation and drywall. Is there any foam board? What about the foundation? Do we have a basement? Do we have concrete slabs? You know, how much of the foundation is showing? There's a variety of things that we're looking at when we're trying to determine where and what our thermal conductivity is. So we know that wind also can be an issue of comfort. If you live in a house in the middle of a field and there's no trees to block the wind, a very windy day is a high pressure system. A very cold, stormy, windy day is going to be creating that wind chill. It's going to be pushing wind towards you and through your house and through your windows. So when we get into heat transfer of systems, we're talking about 2 different types. We're talking about forced convection, which would be if we had a fan blowing air or circulating water through a system. And we have stuff that's like natural convection. Natural convection could be more like an oil heater that you have in your house. I have oil heaters in my basement. I plug them into an outlet. They don't have a fan. They don't do nothing. They just have natural convection. Heat just kind of comes up off of them, but it doesn't really move around the house. It moves around slower than forced convection. So we tend to use forced convection to try to heat and cool rooms more quickly. Okay, so let's move on. When we're looking at two types of convection or heat transfer, we understand that we've got hot water coming in. We blow cold air over a coil. We should get warm air out. When we look in our furnaces, that's what we have. We have hot water coming in either from some type of heat pump, compressor, or solar thermal collector, and hydronics runs out. This isn't always water. If you're using a refrigerant, it could be a refrigerant in a heat pump system, and that's coming in hot too. But we're still blowing cold air over the coil, and we're getting warm air out, but we got to bring a hot air in. So natural convection versus forced convection. This right here, we're not going to focus too much on. This is just an overall view of the electromagnetic spectrum. This is just talking about different types of light. For the purpose of this, you just need to know that some light is got more energy than other light. And some light that shines on your house from the sun is going to heat your house up. It just depends on what type of light is coming through. So any surface continually emits thermal radiation to any cooler surface within sight of it. So we know that when the sun shines on something, it's emitting thermal radiation. It's going to be warmer. Okay, so there's not a whole lot on this page that we're really too concerned with. This, though, is showing you an infrared camera. So now that they've talked about infrared light and electromagnetic spectrum, now we're looking at an infrared camera. What they're looking at there is hydronics in the floor. So they've got water piping running through the floor, and that keeps the floor warm. I'm sure it does a really good job too. As long as the system is built right, that's very nice. It can cost a lot of money though to have some special stuff like that. But we're going to use a thermal imager to try to find where in our building we're losing heat. We're either losing it through the walls, we're losing it through the doors, we're losing it through the floor. We can see right here, they're losing a ton of heat right here around the bottom of the door, but the floor is nice and cozy. And so a lot of this heat is just going to go right up there and cool these windows. So this is where I would put a quilt or something over that window, and then I won't lose as much heat because of that door, that window. Okay, we already talked about thermal equilibrium. Let's move on to the first law of thermodynamics, which we all should know as energy people. So the first law of thermodynamics says, it states that energy cannot be created or destroyed, only changed in form. Okay, so we're going to always need to remember energy cannot be created or destroyed, only changed in form. So what they're talking about is if you have a house or you're burning a certain amount, just say wood, not all of that energy is going to be changed into heat. Even though that wood may have a certain amount of BTUs available to it, it's still going to, a lot of that heat's going to be lost up out through the chimney, as we all know. But at the end of the day, there's still that much heat available that's coming from that source. So we have to do efficiencies, and those things have already been done. We have to do efficiency calculations on all of these different types of energy to be able to be fair. And we're going to learn how to do that. We've got a nice little table coming up here that we'll be working on, and it'll help us understand some of that stuff. Okay. The second law of thermodynamics right there is something that we need to understand. And we've already talked about it. Heat always moves from an area of higher temperature to an area of lower temperature. So make sure you know those two laws of thermodynamics. Then they get into a concept called entropy. And entropy is just a matter of how useful is that energy. Like a solid flame is very useful. We can use it for all types of things. You know, cold air outside, like the air that is outside that might be 30 or 35 degrees, there's heat actually in that air, but we have to use a compressor to get it. But there's heat out there in that air, but it is what we would call, you know, low entropy or high entropy. So depending on the type of energy that we're using is going to determine the efficiency of what we have going on in regards to how we're going to heat or cool our house. Okay, I'll let you read through that stuff there, but that's the gist of it. Okay, so what we want to look at is cost benefit ratios and how to keep a house warm at this point. So if you have, the text is talking about if you want to lower the temperature, that's one way to do it. But if you can't do that, you've got to look at the actual cost of the supply. So we're going to go through an example here. You're going to have a couple examples in your homework. One maybe in this one and one in your next homework, but I'm not going to throw them at you right away. But I want to go over some of the stuff with you to make sure that you understand a cost benefit ratio. So we're going to read this example here. Okay. So we have a family building a new home. They have an option of upgrading the standard insulation package. So we're talking about, do we want to add insulation to our house, or do we want to do something else? So the calculation would show that we would reduce our heating bill by an estimated $350. But the added cost of the insulation would be $5,000. They also have the option of doing solar thermal. That system would save them $650 a year, which sounds better, but its net cost would be $12,000. So those prices can change. That's a pretty expensive solar thermal system, but we don't really know. So all you have to do to get your cost benefit ratio is determine how much your estimated savings would be, which is not easy to do, versus how much it costs. So based on this simple analysis, the insulation upgrade option has a lower cost benefit ratio and is therefore a better investment. So you can see our cost benefit ratio is 14.3. So if I spend $5,000 to save $350, I'm better off going with the insulation upgrade in that sense. If I spend $12,000 and I'm only saving $650, my cost benefit ratio is not as good. Okay, so let's see this right here. So you'll notice that the text right here jumps from page 15 to 27, which is what I wanted to do because I didn't want us to talk about using gray water. They're talking about over the next couple chapters using gray water. That's your sewage water to heat your house. I'm not really interested in talking about that. That's something that's not very common. And it require a lot more discussion. Because right there, they say gray water heat exchangers should only be installed in vertical drainage pipes. That's because that water is it's sewage, right? It's going to stick to the pipes and clog things up. So let's just move on from that. What we want to talk about before we wrap up today, we've been going about an hour. So normally I go 2 hours. We'll be done here within about 15 minutes to half hour. What you want to look at is the price of fuel or electricity or wood, and how would I go about understanding what that means to calculate my heat loss, heat gain. So every type of fuel you're going to have to learn is calculated in a certain way based on its efficiency, how it's sold. We know electricity is sold by the kilowatt hour. We know natural gas is sold by the therm. Now we're going to look at just these examples today, but we can look at the prices of, we'd have to get into digging real hard of what the current price is. But before we get into any of the current prices, we want to make sure we understand how to do this. And I would say the prices that they have in this textbook are well, they go back and forth, but they're good. They're good to give you a better idea, an example of how to do a cost benefit ratio to find out which fuel is going to be the best for me. Should I use wood? Should I use electricity? And then what else can I do? Now, some of the stuff that can be done can make a huge difference. You may do a calculation where you have electricity as being the most expensive, but if most of that electricity is being made from a solar system, then maybe it's not, because that's free energy depending on what your cost benefit ratio is. If you pay $20,000 for your solar system, how much is it saving you a year? Well, you can do a cost benefit ratio on there. If it's 20,000, it's saving you 2,000 a year, your cost benefit ratio is 10. And so right there, you're at a much lower cost benefit ratio. So what we want to do is get an idea. You want to have an idea of how much. So my question to you guys is, what do you guys use to heat your houses? I know I've been talking a lot. Does anybody use wood pellets to heat their home?
My uncle used to use that. He had like a furnace outside that he'd put pellets in or other wood.
So did mine. Yeah. Pellets, wood pellets. Okay. Um, what what else do you guys use to heat your home? You use natural gas, I'm assuming. Does
I do.
anybody natural gas? Okay.
Yeah, we have natural gas.
I mean, I think
I
most
use
of us.
electric.
You're electric. Okay. I'm electric too. I'm electric. Some people use propane. It's a lot like natural gas, right? But it's going to cost different. I used to use propane. And then one year it went crazy. It cost me so much more money. I didn't want to use propane anymore. But that's going to depend on where you live. So what we need to understand is what the costs are. Like wood pellets could be calculated by ton, by pound. We need to get a way to do this. And so the textbook, I think, does a really good job of helping you understand this. I mean, it's very complicated, but understanding how to do this. So what they do is we take these units and they put them into dollars per millions of BTUs. So dollars per millions of BTUs, or delivered heat. How much heat can this fuel give you per the cost? So what we have is this little chart here. And I'm not going to make you do this chart today. Your next assignment is going to have this chart on here. So you're going to have to refer back to this lesson to do that. And I'll reiterate that. But what you'll have in your homework, your next homework, is you'll have this chart. And you're going to have to pop in some numbers and do some of these calculations. Now, how would I do that? That's the question. Well, it's pretty easy because this is worked out for us, but you do need to pay attention to some of what these abbreviations are. Like most of the time, they're just efficient or performance ratings that you're going to have to find from, say, a manufacturer. What is your COP? So you got an electric heat pump with a seasonal average of a coefficient of performance of 2.5. That's what you need to do, because you're going to have to put that number 2.5 right here. And then you're going to have to find out how much does it cost per kilowatt hour? Well, they're telling us this electric resistance heat is 12 cents a kilowatt hour. That's pretty close to what most of us pay. That's good enough. So we would have to put 12 cents in there, 12 cents in here, whatever we could find out. Now let's take some time and let's take a look at on the next page. Well, I got this right here. Let's look at that. It's 12 cents for your electricity. You got your coefficient for your heat pump. You also have fuel oil. It's 300, according to this at this time, it's $3.50 per gallon. It has an efficiency rating you need, 83%. Propane at $2.75 per gallon. It has an efficiency rating. Natural gas, it has, now notice your efficiency rating is going to stay pretty much the same. And firewood. Now firewood's a little bit different. It has a 60% seasonal heat source efficiency number that you got to go along with that, because so much of your heat is lost up your chimney with firewood. Wood pellets, $275 per ton. Then we see coal. Coal is $150 per ton. And then lastly, shelled corn is $9 per bushel. So we can also use a corn burner. So we can burn corn, we can burn wood pellets, we can burn firewood. We can also burn coal if you got coal and you can get your hands on coal. But as we know, it's very dirty, and we've gotten away from that with natural gas because it's cleaner. But people used to burn coal 100 years ago in their homes. And does anybody have any relatives that still burn coal? I imagine you probably do not. Depends where you live. So let's see what the numbers are telling us. So what they did is they put 12 cents in there, and they come up with this number, meaning $35.16 of millions per BTU. When we look at this number, the lowest number is the best. So what do you find interesting about this? Which is the best one? You guys see that?
Coal.
Yes, coal by quite a bit. So $5.91 costs $5.91 per millions of BTU. Okay, to make a million BTUs, it costs you $5.91 with coal. With electricity, it costs $35.16 to make. Now, all you can do is lower that cost. Now, you can use, that's electric resistance heat, though. That's going to be like baseboard heaters or heaters that you plug into your outlet. I have a heater in my office right now, and I'm doing that. It's costing me a lot of money to run that heat. Heat pumps, though, are going to be a lot better because they have a much higher efficiency, even though they are electric. So in that case, we take our 12 cents times our multiplier over 2.93, which is going to give us our conversion into BTUs. And we got to go by our heat pumps number. So the one they gave us was 2.5. This is a pretty efficient heat pump, to be honest. And I have a heat pump in my house. I have 3 heat pumps. They tend to work pretty good until it gets to be about 10 degrees. Then they don't seem to be working much anymore. You know, it's getting scary at that point. So that's another reason why I have a wood stove to help me burn firewood. Fuel oil can be expensive because we're talking about crude oil. Most people don't burn fuel oil. So it's $3.50 a gallon. That's pretty high. Propane, as you notice here, propane per gallon can be pretty high too. That's been my experience. It can go down. That's one of the problems with the fossil fuels, is the fossil fuels are always going to go up, just like gasoline does. Just because as the world creates more demand, then there's going to be less of it available, and then it's going to go up in price. And you may have those times where they find a nice reservoir and we can get a little break for a little while, but we can count on it to continue to go up because it's not renewable. Now, natural gas can be renewable depending on where you get it. If it's coming from a landfill or coming from some other place, it's just not something that we plan on using. Well, we can run out. Everybody can't be using natural gas. So we notice that number right there is 15. So that's why most of us are on natural gas, because it costs $15 per millions of BTU. Firewood, that's surprisingly efficient. especially if you get it for free. So that's if you're paying $60 a cord. That's something that I don't know. That's hard to find stuff that cheap anymore. But you can also chop your own firewood, and when you do that, you're definitely getting yourself into a situation where you can save some money, but you're doing the work. Wood pellets, surprisingly, are costing a little bit more. And we notice coal is lower, and then shelled corn. So one of the problems with going with the pellets and the shelled corn is that you got to go and buy them by the bag. And it depends on what they're charging you per bag if you get all invested into that. Same with coal. But, coal, depending on the area that you live in, it's just you can find it in certain places very, very, very cheap. Okay, so what we're going to do is look at a situation and determine who is going to be better off. Which type of energy should we use? So in this example, and this will be our last example, and we'll be done after this for today. And then all you need to do is just finish up your homework, and you'll be all caught up until Monday. But we have an example. We have an 1,800 square foot house. It's fairly new. The owner wants to select a single fuel to provide space heating and domestic water heating. And so we're going to use the methods that we discussed. Now, they were able to convert that they are using 37 million BTUs per year. So if you can determine, let's say you have a house and you use, you use 100,000 watts a month, over 10 months, you're going to use 1,000,000 watts. And then you can take those watts and convert them into BTUs with a calculator. That's how you can find out how many BTUs a year you're using. That's one easy way. And you have domestic water heating as well. So you take and combine all that stuff together, and that's going to be the total number of BTUs that this one person is going to need to be able to keep that house warm. So we get some new options. They say, well, the electric heat went up. It's 13 cents. It could be they live in a location like Hawaii where everything costs more. It is, not everything is cheap in Indiana as it is in other places. But that's pretty close to Indiana prices. They have a heat pump with the COP of 2.5. They have their fuel oil option, their propane, natural gas, and firewood. $70 per cord. Then what they do is just, what is your basic service charges? That's stuff that you can kind of ignore if you want, unless it's something that's built in there already. So you've got $16.50 per month for electricity. You got to add to that cost. And then if you have natural gas, you got to add that. And that's true. You get a lot of fees added on top of everything else. So if you're like basing this off of just your energy usage and not counting any of the fees or the service costs, you could be off a little bit in your numbers. Whereas in wood, if you got trees, you can cut them down, but then you got to, how much gasoline, how many chainsaws do I go through? You got to think about some of those things. And most of that stuff's that's just hard. That's just hard work is what that is. So let's take a look. So now they take their numbers and they put, we know 13 cents is going to be too much. So $38 per million BTUs. Heat pump is still at 13 cents, but it's going to be much more efficient to run a heat pump instead of electric resistance heat. So that's at 15.24. We know fuel oil is going to be high, so fuel oil is not a very good option. Propane depends on the price per gallon. That could be, or it might not be, it's volatile. Natural gas, that one they got only at 65 cents a therm though. They dropped that down quite a bit, but that's the volatility of, you know, the cost of things. And so I expect the cost of everything to go up. We're in a state of inflation right now. So natural gas shouldn't be going down, it should be going up. Then we have firewood. So we see at the end of the day that we can calculate each one of these fuels individually and have a better understanding of how many millions of BTUs that we're going to be able to make and create at a cost. And it's not too difficult to do with this formula here. So what we understand is that this family has a total of 49.6 million BTUs a year that they need. How do we figure out, lastly, if we're going to use one fuel versus another, how much it's going to cost? That's where this chart comes in. We look at this chart, we see each one of these costs per millions of BTU, and then we're going to take it down there and simply multiply it. So that's how much the family uses. That's how much it costs per millions of BTU. That means if the family uses electric resistance heating, they're going to pay about $1,800 a year. If they have a heat pump, they're going to go into this with half that much. So heat pumps are good. Then we have fuel oil being quite high, propane being quite high. We're going to see probably natural gas being the best right there. And that's really cheap for natural gas. And so they had to add in their electric service as well. And we look at wood. We get a better idea that that's only at $690 per year. So it all depends on what fuel source you're using and how much of that you need. Okay, any questions on any of that? I know it's not the most fun stuff, but that is all that I have for today's lesson and your first lesson. So all you really need to do is come in here and fill in this homework here, answer these 12 questions over that lecture that we just did, and you're off and going into this class. Are there any questions for me before I let you guys go?
For next Wednesday, we're going to which location on campus?
We're going to always meet at the ENRG Center, Craig Porter Energy Center. Okay, so that's on Wednesday, starting next week on Wednesday. And then if we're going to go climb or we'll go from there. We'll drive down to the other building if we have to, but I don't want to cause too much confusion. We'll have to discuss it. Any other questions? Okay, well, that's just your first introductory lesson to residential energy basics. And next week, we're going to have to get into some stuff that's a little bit tougher. And I'll work on trying to make that as easy on you as I can. And then we'll be able to also do some application with that when we get on campus. So that's when all that stuff will start to click. Okay, well, if there's no questions, good luck on your homework, and I will see you guys back at our Zoom meeting on Monday when we start next week. Have a good day.
Bye. Thanks, John.
See you, John.
Yep.
All right.
Bye, guys.